All right, guys, let me just draw out as an example what I mean by resonance structures being not in equilibrium with each other, but basically a depiction, a cartoon of the real molecule. So as an analogy, imagine that I want to show you my cousin, right? I mean, my nephew, Benjamin. He's a 7-year-old boy, and I want to show you his personality. I want to convey to you what Benjamin is like. Instead of drawing Benjamin, I draw some kind of cartoon character, right? That you might be familiar with, that means something to you. And so this cartoon character alone, however, doesn't completely describe what Benjamin's like. I actually need to draw another cartoon character and use this double-headed arrow. This is called a resonance arrow. This arrow is totally different from the equilibrium arrow, right? This arrow has 2 heads. It means that these 2 structures are actually trying to depict the same real structure. They're 2 cartoons, 2 imaginary structures that depict the real molecule. And so in this case, a mixture of Charlie Brown and a mixture of Bart Simpson best describes my nephew, who's a real boy. Okay, so this is sort of what resonance theory is about. It's not that Charlie Brown and Bart Simpson are in equilibrium, right? Benjamin's not jumping back and forth between the 2 of them. He's actually a hybrid. He's a mixture of both. And I could even say that he's 70% Charlie Brown and only 30% Bart Simpson. And so resonance structures in a similar way can have different weights, right? One resonance structure can be much more important than the other. And as a result of that, we can also understand the real molecule in more detail.